Hello everyone. Today I'll discuss the innovation performed by me using the graphical LCD module and the 8085 microprocessor. So let us first understand what is a graphical LCD and its importance. A graphical LCD is a type of display module that allows individual control of every pixel on the screen, unlike character LCDs which only show predefined text or characters. In our experiment, we have used a resolution of 128 into 64 pixel display. So internally, a graphical LCD is divided into two halves, and it is controlled separately by a controller chip select. The display is again organized into paging schemes. We have 8 pages, page 0 to page 7, and each page is 8 pixel tall. So a page consists of 8 into 64 pixels. So to write anything on the screen, you must first select which half, then the correct page, then the correct column, and then you send a data byte. A data byte consists of 8 bits, where each bit represents one pixel in that column. So this high-level pixel control of the graphical LCD makes it highly suitable to draw graphs, custom characters, or even patterns. And it finds its application in many devices using like mobile phone games, handheld games, even lift indicators. So what was our original lab experiment? Our original lab experiment consists of simply displaying a text and a border, which we'll look into now.
Today I've performed the graphical LCD module experiment. Over here the experiment will run to show a square along the borders and to display Excel technologies in the center. So we can see the square formed along the border, top and bottom, and Excel technologies being displayed in the center.
So as seen in the experiment, it only displayed a static character. But what if we want to display something dynamic? Is that either the text is moving or it is blinking? Blinking text has various applications. You can see them in pedestrian signs, you can see them in washing machine or even uh, microwave screens, you can see them in alarm clocks. So yes, there are applications of blinking text. But how do we build the logic? You first display the text, then you hold the text using a big delay, then you clear the LCD, and you hold this cleared LCD for a big delay, and then this loop continues. So it is very important to understand delays. In order to create a very big delay, there are various methods. But how do we select the right one? The first method is using a single register counter. In this method, a register is initialized with a value, then we decrement the register, then we check if the register has become 0 or not. If it is not 0, then the loop continues, and if it is 0, then we come out of the loop and the program continues. So now let us get into the mathematics of it. Each of our mnemonic over here consisted of some machine time cycles. The code outside the loop is given in blue, and it consists of 7 T cycles. So the time taken by the code outside the loop is simply just 7. Now for the code within the loop, we have 4 T states plus 10 T states, so this is in total 14. But since we have initialized C over here with the value FF, which translates to 255 in decimal, this loop runs about 255 times. So we multiply 14 into 255. We do a small collection of -3 over here because over here this conditional statement is of 10 T states only when the loop is run again. But it is actually of 7 T states if we jump out of the loop. So this is how we get the total T states. Assuming over here for all our further calculations that we have taken our clock frequency to be 2 megahertz, we multiply it by the inverse of that to finally get approximate of 1.8 microseconds. But over here, this delay is very small because the maximum amount that we can store in a single register is only 255. So now you might think, what if we use two registers? Yes, so now we'll move on to the method 2, which is using two register or a register pair. In this register pair, we can store much bigger value. In our example over here, we are storing 1000 in hexadecimal, which gets converted into 2 raised to 12 in decimal, which is 4096. So now we know that this loop will run at least 4096 times. Then we do a similar calculation of calculating the t-state value outside the loop and inside the loop. We can see over here that for a single register, our calculated value was 1.8, but for a registered pair, we get it as 49 microseconds, which is 27 times much longer, which is a good increase. But what if we want more? Now we go on to method 3, the method that I have used. It is a method of nested loops, where over here now the delays don't get added up, but instead they get multiplied. We use an outer loop over here indicated by blue and inner loop indicated by green. The outer loop, in the outer loop we have initialized b with 256 as value, and in the inner loop we have initialized b with 256 value. So the outer loop actually runs 256 times, and the inner loop runs 256 times per outer loop. So now we get 256 into 256 iterations, which is a very large number. We similarly do a delay calculation and get a very large value of 460 microseconds, which is a very visible blink. Now let us get into this delay subroutine and understand each and every mnemonic in it, because this is the subroutine I have used in my innovation. So we have taken an outer loop and we have given it the name big delay, and we have initialized B with 00H, which stores 256 passes in this. And then inside this big delay, we have stored C, and it has 256 passes again. In the smaller loop, we now decrement the value of C till it becomes 0 using this condition of jump if not 0. Then we finally come out of the inner loop and go into the outer loop where we decrement the value of B. And then we again check if the value of B has reached 0 or not using jump if not 0 condition. And then this loop runs about 256 times, and then we finally get out of the loop and return to the main function. So now let us carefully see where I have modified in our existing code. So this was the original program. Over here, we were supposed to display Excel technologies at the center with square border on the top of and bottom. In my innovation, I've kept the subroutine to clear the LCD same as it is, and also I've kept the subroutine to display Excel technology same as it is. The main changes have been made to the main method, and I've also manually typed the new subroutine for the big delay. So instead of the halt mnemonic over here, we'll now change it to add loops and calling all our other subroutines. So this is the modification made over here. We can see that instead of putting halt in this address, now we have called the big delay. Then we have called clear LCD subroutine. Then we have called the big delay subroutine again. And then we have finally jumped back to this address, which calls our Excel technologies. And this is the same big delay subroutine as shown earlier. So now let us look at the innovation performed.
Many conditions, people would prefer that instead of a static display, this display is dynamic, is that this display moves. For example, if you want to do a blinking display, we would like to introduce a very big delay between clearing this LCD and then displaying this text. So let us run the program for it.
And therefore, we have seen that even though such a blinking text modification is very simple, it holds application in various devices. Thank you.